purpose of this tutorial is to introduce you to the key elements of the lighting tab. The data entered in this tab governs the lighting performance and associated energy consumption, but can also have a significant impact on internal heat gains. During this tutorial, I'll review the lighting template selection and key data inputs, daylighting controls, and using two daylighting sensors in one zone. During the tutorial, I'll run some simulations to compare results before and after changes are made. Going to the Lighting tab, we can see that the reference lighting template is loaded. The default template has a relatively high energy consumption of 5 watts per meter squared per 100 lux, which will be multiplied by the target illuminance for the zone. So for example, where our offices have a target illuminance of 500 lux, set by the activity template under the lighting header here, this will result in a lighting energy consumption of 5 times the watt per meter squared per 100 lux value, or 25 watts per meter squared in this case. Also note that the reference template has no lighting control enabled. Prior to making any changes, I'll quickly review a few of the key simulation results for an hourly simulation run during the summer design week. At building level, we can see that the fuel consumption for lighting systems is a constant value of around 26 kilowatts, which would indicate that the lighting is basically on during occupied hours. All of the office zones are set to the same activity, and most are the same plan area. Therefore they show a constant internal gain from lighting. Going to some of the zones, we can see that this is around 6 kilowatts, and that the lighting often provides the highest internal gain by some margin. Going back to the lighting tab at building level, I could change the individual parameters here, but in this case we'll load the best practice template which will automatically load the best practice lighting parameters in the headers here below. Immediately you can see that the energy consumption has reduced to 3.3 watts per meter squared per 100 lux, which is more realistic for a new installation. You can of course change this to another value using the slider or the arrow controls. If you feel you require more accuracy than these controls permit, you can uncheck the slider controls option in Program Options here to enable you to type in exact values. The Open Plan Office operating schedule here is loaded by the activity template, which, as we saw from the graphs, just switches the lights on during normal occupancy hours. After highlighting the schedule, we can see in the info panel that the lighting is scheduled on from 7 AM to 7 PM. Time schedules will be covered fully in a later tutorial. We can change the Luminaire type using the drop-down menu here, which in turn changes the radiant and visible fractions here and the associated performance characteristics. Task and exterior lighting can be switched on using the checkboxes and the details amended as appropriate. I'll now move on to cover daylighting controls. Loading the best practice lighting template has switched on the lighting control here by default, which enables the model to reflect the reduced energy consumption associated with a daylight control system. The model will reduce artificial lighting levels to maintain the specified illuminance level based on the availability of natural light at the sensor location at each time step in the simulation. This option can only be used in zones which receive natural daylight and should be switched off in zones which receive no daylight. We can select either the linear off or stepped control option. As we can see from this graph in the help file, the linear control type will vary the lighting power input linearly according to the available daylight illuminance, but will stay on at the minimum power input when the target illuminance level in the activity tab is reached. The linear off option operates in the same way, but switches off the lighting when the target illuminance level is met by daylight alone. The stepped control option will vary the input power to the lighting in a stepped rather than smooth linear manner according to the number of steps specified. This graph in the help file shows 3-step control. But we can specify the number of steps relevant to our system here. I'll set the control type to linear off. The glare index is used when one or more windows in a zone have shading devices which are set to operate according to glare. 2 lighting areas with their own sensors can be specified in each zone if desired, although the default setting is 100% control by 1 lighting sensor. Going to the office zones, we can see that the single sensor is centrally located in each zone by default. Here are the results of a further simulation run with daylight control enabled. You can see that the previously constant 26 kilowatts energy consumption has reduced markedly. The internal gains have also reduced significantly from the fairly constant 6 kilowatts produced initially. You'll also notice here in the western zones that there's still an artificial lighting demand early in the day, when daylight levels are low, but the daylight controls have eliminated the demand in the afternoons. The converse is true in the east zones, when daylight levels are generally higher in the mornings. Overcast days have lower solar gain and daylight illuminance levels and therefore require more artificial lighting. Specifying 2 daylight control areas enables you to use different sensors to control the front and back areas of deeper plan zones, or where you have different daylight illuminance levels at any one time, created, for example, by external glazing on one side of a zone and internal glazing from an atrium on the other. I'll now add a second sensor in the ground floor west office zone to optimize daylight control in both areas of that office. I set the target illuminance to that specified in the activity template. The sum of the percentages controlled by each area must not be greater than 100. So I'll set them to 60 and 40% for sensors 1 and 2 respectively. If the total percentage controlled is less than 100%, the remainder will simply be controlled from the schedule with no daylight control. I'll now go back to the zone and move the sensors to the correct positions, with sensor 1 controlling the larger zone and sensor 2 controlling the smaller zone. In this tutorial I've reviewed the key elements of the lighting tab, and we've seen the beneficial effect of enabling daylighting controls, possibly using multiple sensors, to minimise energy consumption and the associated internal heat gains.